Good evening, everyone, and welcome to the 10th problem-solving session of the course Computational Continuum Mechanics. So till the last session, we were looking at concepts of hyperelasticity, constitutivity, and then these the balance laws. So right now, we'll be starting off with linearization, which is at the heart of any computational methods in mechanics, nonlinear mechanics. So let us start with that. So first thing is, okay, so just a minute. Yeah. So this week we look at the concept of linearization. Okay. So this week's assignment, I have taken a look at this week's assignment. It has mostly theoretical questions. You don't have any problem solving. So most of them are conceptual questions where you have to answer things like whether something is true or false and that kind of questions. So a conceptual revision of whatever was done in this week will be useful. Therefore, what I am going to do is I'm going to split up the process of linearization of the virtual work principle into some number of questions so that you can refer to them. So the first thing that we look at is the equivalence of equilibrium conditions or equilibrium equations and the principle of virtual work. Okay, so we'll start with this. So first question today will be to show that the principle of virtual work is equivalent to the equilibrium equations. So first, let us start with what is the equilibrium equation in locals? So it is the divergence of sigma plus rho b is equal to 0, where sigma is the Cauchy stress, this divergence of something is the del by del xj. If you have a vector field, it is Vj. Right, this is the divergence operator. And this divergence is with respect to the spatial coordinate. Rho is the density, the current density. So this is the current density in the deformed body. Therefore, it is a function of x, the spatial coordinate. B is the body force per unit mass. So B, since it is per unit mass, it doesn't matter whether it is in the reference body or in the spatial body. So this is the equilibrium equation. This is the balance of linear momentum when there is no acceleration. So under quasi-static conditions, this is the equilibrium equation. Now, we claim that this is equivalent to the principle of virtual work, where we say W internal is equal to W external, or del W internal is equal to del W external. So this is equilibrium equation. And the principle of virtual work is as follows. The virtual work done by the internal virtual work done is equal to the external virtual work done, wherein the external virtual work done is defined as the work done by the tractions and the body forces on an admissible virtual velocity field. So you integrate the so you have tractions on the surface of the body. Integrate take a dot product with the velocity field, with a virtual velocity field, with an admissible virtual velocity field, and integrate it throughout the surface. So that will be the work done by the tractions, and you also have the work done by the body forces. So we have the body forces; they are everywhere in the body. So integrate over the entire volume. And what is the work done by the body forces on the virtual velocity field? So this is the external virtual work done. And the internal virtual work done is what? The internal virtual work done is so it's actually virtual power, because it has got the units of work done per unit time. Therefore, this has got the units of power, so I can call it virtual power, but it doesn't matter. You can call it virtual work done. So the internal virtual work done is nothing but the Cauchy stress double contracted with the rate of deformation tensor T. So these two are completely different statements, and this should hold for all. So this is the virtual, sorry. So this is the virtual rate of deformation tensor, which is associated with the velocity field del V. And this is over the entire volume V. So, and this should hold for arbitrary virtual arbitrary admissible virtual velocity field del V of x. So what it says is that we have a body, if we have a body that is under equilibrium, that's under static equilibrium, under the action of certain tractions T and body force B. So if we have a deformable body at any instant, which is under static equilibrium, when subjected to a set of traction force T and body force B, then the virtual work done by the external virtual work done by the traction and the body forces on an admissible virtual velocity field delta B is equal to the internal virtual work done by the stresses on the rate of deformation tensor associated with the virtual velocity field delta V. So, so what it means is that this delta D is obtained as the symmetrization of gradient of del V. So del V is not any differentiation of the velocity field. It is just an admissible virtual velocity field. So what do we mean by admissible? By admissible, we mean that wherever we have the displacement specified, there this we cannot have a velocity field, right? Because if you specify the displacement, that you cannot have a velocity field there. We are specifying the boundary condition there. Suppose we have on a part of the boundary, we are specifying the displacement to be 0 or displacement to be fixed at some value. There we cannot have an admissible virtual velocity. So this is the statement of the theorem. We have this equilibrium the condition for static equilibrium at every point in the body is equivalent to saying that the external virtual work done by the tractions and the body forces on an admissible arbitrary virtual velocity field should be equal to the internal virtual work done by the Cauchy stresses on the virtual rate of deformation tensor associated with this field. And this should hold for all admissible virtual velocity field del V. So how do we prove it? So the solution is as follows. So there it is equivalent, means we need to show the proof in both the directions. So first is you say divergence of sigma plus rho b is equal to 0. In initial notation, you can write it as del sigma ij by del xj plus rho bi is equal to 0 for every I. 1, 2, 3. And then so we can integrate it over the volume, say dou sigma ij by dou xj. So first thing, this, so you need to do, so sorry, so you need to get, this is force equilibrium, right? This is statement of equilibrium of forces, and this has got three components, I1 and I going from 1 to 3. So it has got three components. But what we actually want is it's a scalar equation. What we have here, it's the virtual work done, which is a scalar. So dot product it with velocity. So how do we dot product it with velocity? So this, we can call it as a residual force, right? So this you can say it has a residual is equal to 0. Now, this, what is it a function of? This is a function of the deformation. So if you have a deformation, xi is equal to some chi of capital X, right? So this is chi I of capital X. So this is the deformation field. So once we know the deformation field, that is x1 is equal to x1 of x1, x2, x3, and t. Similarly, x2 is equal to x2 of x1, x2, x3, and t, where capital letters denote the quantities, capital letters denote the coordinates in the reference body, and the small letters denote the spatial body. So this specifies a motion. Now this mapping, you can call it as chi. And once you have this mapping, you can define the deformation gradient as gradient of the sky. And once you have this deformation gradient, you can find everything else, such as the green Lagrange strain tensor. And from the green Lagrange strain tensor, if you have some constitutive relationship like this, you get this second Piola-Kirchhoff stress. And if you get the second Piola-Kirchhoff stress, you can get the Cauchy stress as so how do you get Cauchy stress? It is J inverse Fs F transpose, right? So you push forward S and then do a scale it by J inverse. So this is fine. So which means, so if we find the motion, so what this means is, if we find the deformation or motion, then we get everything. We get the entire strain distribution, stress distribution, forces, etc., etc. So suppose suppose chi is the actual deformation field. By actual, we mean that chi is a deformation field that keeps the body in equilibrium, that satisfies the equilibrium condition. So this is the actual deformation field. What is the residual of chi? So the residual of chi will be del dot sigma of chi plus rho b of chi. This will be equal to 0. However, if we take some chi tilde, which is not equal to chi, then the body may not be in equilibrium in general. So for other cases, the residual will be non-zero. Now, what is our objective? We want to find chi such that the residual r of chi is equal to 0. And r, we are defining it as the divergence of sigma plus rho b. So if this thing is actually 0, then if you take a dot product of r with an arbitrary velocity field, then it should also be 0 for all arbitrary admissible velocity fields. So this is some set of all admissible velocity fields, right? So this basically means that, and if you can also integrate it over the volume so that you get a scalar. So integrate it over the entire volume. So that is basically it. So you say integral divergence of sigma plus rho b dot product with the velocity field, the virtual velocity field, integrate over the entire volume should be equal to 0. Now this is a scalar equation. You don't have three components. You are dot producting it with another vector field so that you get a scalar field. So this is a scalar equation. Now write this in indicial notation. You have dou sigma ij by dou xj plus rho bi. So this is the ith component of the first vector. Then you have a dot product, so you'll get an ith component of the second vector. So this will be equal to 0. Now, can we simplify this further? Yes. So you can split the two terms. You get a dou sigma ij by dou xj vi plus rho bi vi dv is equal to 0. So what do we do next? The second, this term can stay as it is. Look at the first term. So dou sigma ij by dou xj del vi. Okay, there's a del I'm missing out, but it's there everywhere. So there's a del vi, del vi. This is equal to, using the product rule, you can write it as dou by dou xj of sigma ij vi del vi minus dou sigma ij dou by dou xj of del vi. Right, so this is basically the product rule. If you take it to the other side, it's just the product rule. So you have a product of two terms inside. Del vi is an arbitrary velocity field. Sigma ij is the Cauchy stress field. You're taking a derivative with respect to xj. So first you differentiate with respect, differentiate sigma and keep del vi constant. Then you differentiate del vi keeping sigma ij constant. So you get two terms. Now I'm just shifting it to the other side. So this is a simplification for the first term. It's not a simplification, it's actually bigger, but it's fine. So this is the first term. Let us replace the first term by that. So you get integral over the volume. You get the derivative with respect to xj, sigma ij vi minus sigma ij dou vi by dou xj. So I have dropped the del symbol, but it's there. Just remember, it's there everywhere. This integrated over the entire volume plus v rho bi vi dv is equal to 0. Next, look at the first term. So this is nothing but dou by dou xj of something integrated over the entire volume. Here you can use the Gauss divergence theorem so that this becomes an integration over the entire volume. Is dou by dou xj. So the shortcut to remember this is whenever you have something with respect to xj, replace that derivative with respect to with nj, which is the jth component of the normal, to the surface at any point nj, and keep the argument of the derivative as it is, sigma ij vi. ds, it's integrated over the surface, minus integral sigma ij. What is dou vi by dou xj? It is lij. It is the velocity gradient lij dv. And this is integrated over the volume, and you have rho bi vi dv. And this is equal to 0. So take the negative term to the other side. What is sigma ij nj? It is the traction ti. So we get dou v ti vi ds plus integral over the entire volume rho bi vi dv is equal to integral over the entire volume sigma ij lij dv. So so this is about every term is a dot product, so you can get back to the vector form. So it is t dot v ds plus integral over the v rho b dot v dv, and this is equal to integrated over the volume. This is a double dot product. It's a double contraction between sigma and L. But what is L? L has a symmetric part which is D, and it has got an anti-symmetric part W. But sigma is a symmetric tensor. So we know that sigma double dot contracted with W is what? It is also sigma contracted with sigma transpose contracted with W transpose. But sigma transpose is nothing but sigma, and W transpose is minus W, which means sigma contracted with W is negative of itself. Therefore, sigma contracted with W is 0. Therefore, we are left with so this will not contribute, and we'll have only the contribution from D. So you can write this as T dot. So V is actually del V. I'll get back to the del notation. Del V ds plus integral V rho B dot del V is equal to integral over the volume sigma double dot with del D. So D, yeah. So what we have on the left hand side is the external virtual work done, and what we have on the right hand side is the internal virtual work done. So this is fine. So this, what we have shown is that, and there's nothing special about the del V that we have chosen. So this should hold for arbitrary del V. Now, so you can reverse the steps. You can easily reverse the steps and then also arrive at this. So if you start from here, if this is given that for arbitrary del V this has to hold, you can reverse the steps. You can reverse the steps up to this point. And then you can say that this has to hold for arbitrary V. So you can choose del V as 1, 0, 0, 0, 1, 0, and 0, 0, 1, so that you will get the three equations of equilibrium. Three scalar equations or the one vector equation of equilibrium. So that is simple. That can be done. Now, so the first thing, okay, so this shows that. So first we have shown equilibrium implies, if we assume equilibrium, we are implying principle of virtual work. To show the converse, reverse the steps. Therefore, equilibrium and the principle of virtual work are equivalent. So what is the second task? So this is done. This is done. Now let's look at the second thing. So to solve any problem in mechanics, to solve a problem, to solve a nonlinear mechanics problem, means to find the deformation x is equal to phi of, let's call it phi. So essentially, if I say I have solved a problem, it means I have got the deformation field as a function of x and t. So this is what solving a nonlinear mechanics problem means. So if I get the deformation mapping phi, as I said, I can get f, I can get the strains, I can get the stresses, and everything else follows. So solving a problem means once you get the deformation field, we get everything else. But if you look at the so what is the governing equation? The governing equation is that of equilibrium, and so the governing equation is equilibrium equation, or equivalently you can also say it is the virtual work expression. Internal virtual work done is equal to external virtual work done for all admissible velocity field del V. So this is the governing equation. We have to ensure that the internal virtual work done by the Cauchy stresses on the virtual rate of deformation tensor is equal to the external virtual work done by the traction and the body forces on the velocity field for every admissible velocity field. But this is a highly nonlinear equation. This is highly nonlinear equation. How is it nonlinear? Let us see. So suppose we have a relationship between. So what appears in the equation? We have to show. We have to ensure. We have to solve this. We have to solve for T dot del V integrated over the entire surface plus B dot del V. There's a rho B dot del V integrated over the volume is equal to the stress power sigma dot del D integrated over the volume for admissible del V. But if you see, the integrals are over the equation itself is over the deformed volume. So this is the deformed volume, which itself is a function of the deformation. Right? If we know the deformation only, we can know the deformed volume. Therefore, we don't even know what the limits of this integration are. They are over the deformed volume, so we don't know that. Then if you look at, so externally, we can say the traction and the body forces are specified. That's not a problem. Del V is arbitrary, even that is not a problem. But if you see this term, you see sigma is a function of it could be a function of some, so I will use the response function notation. It is a function of, or okay, let me say sigma is actually J Fs F transpose. It is the push forward of S. And this S itself is some function of the green Lagrange strain tensor. And this green Lagrange strain tensor is what? Green Lagrange strain tensor is half of F transpose F minus I. So this green Lagrange, and F is what? F is the del xi by del xj. So this is Fij. So this is linear in. So F is just the gradient of the deformation. So this is linear in the deformation. Some phi of x. So this is linear in the deformation. But if you see the green Lagrange strain tensor, it is not linear. It is non-linear in F. Hence, non-linear in S as well. This relation in general can be non-linear depending on what material we are using. This can also be non-linear. And this, you see, it has got a product of F, S, etc. So each of these terms, this is non-linear, this is linear. So you have, even if everything is linear, you have this product which is highly non-linear. And J is also non-linear in F. So this relationship is therefore this sigma is a highly nonlinear function of this. But how do we solve for this then? So then therefore instead of, so yeah, so we have to solve for this. We have to ensure that this is satisfied. So let us call this as some. Let us call the difference between left hand side and right hand side as something. So let's say W external minus W internal is equal to some R I have already used, so I can just use R. So here it's a scalar R. Now my objective is, I'll use a capital R maybe. So my objective is to set to get, sorry. So this is the residual. If and this residual, as you see, so suppose I have the actual deformation field which satisfies the equations of equilibrium, then the residual of the actual deformation field will be, so this residual depends both on the deformation field as well as the virtual velocity field we are looking at. So it should hold for all. So this will be 0 for all admissible delta V. Sorry, delta V. If phi is the correct solution, if phi is the actual solution. But in reality, we can have, suppose we make a guess. We make a guess P is equal to some phi k. Right? Then R of phi k comma del V will not be equal to 0 in general. So what is our objective? Well, for every delta V, we want to make this residual 0. So here we use the Newton-Raphson iteration. We use Newton-Raphson. So what does it say? Can we get a better estimate? Can we get a better estimate? So the answer is yes, right? So suppose you take in the 1D case, we know that if we have a nonlinear function like this, and you take a point, this is the actual solution. Suppose this function is some f of x. This is x. So this is the point where f of x is actually 0. But if we want to locate this 0, if you want to locate this root of this function, Then we start with a guess. So this point can be some xk. So if we are given a guess, we approximate the rule by the point where the tangent to the curve actually crosses 0. So this is the tangent to the curve at this point. So this line has got a slope f dash of x. So this, how do we say? This is, suppose this is xk plus 1. It's an improvement over xk. So suppose we are close to the root and we have a point, we are having a guess xk. Can we improve the guess? Yeah. So we approximate the root by taking the tangent. So we want, so suppose, uh, suppose xk is, suppose xk is some, or x, suppose the actual root x is some xk plus some delta x, right? Suppose x, and the actual root is x plus xk plus delta x. We want this f of xk plus delta x equal to 0. So this you can expand it using the Taylor series as f of xk plus f dash of xk delta x plus f double dash of xk by 2 factorial delta x square, and higher order terms. This should be equal to 0. But again, this is non-linear in delta x, so we can't do anything. Let us try, if we are fairly close to the root, this can be neglected. So we come up with an improved estimate, which is f of xk plus f dash of xk delta x equal to 0. So we get delta x as minus f of xk by f dash of xk. So an improved estimate is obtained as xk plus 1, which is xk plus delta x, which is xk minus f of xk by f dash of xk. So this is the 1D case. In our case, what we have is we want r of some xk plus u to be 0. So instead of so here we have a scalar function of a vector unknown. This is the unknown vector. Suppose we have a guess xk and we want to reach the actual solution from this. You displace it. You have a displacement u, and we want to set this equal to 0. Now, from the idea of directional derivatives analogous to the Taylor series, we can say this term is nothing but r of xk plus the directional derivative of r of xk in the direction u plus higher order terms is equal to 0. So this is exactly the same as uh, this. Only difference is the argument, the unknown is a vector. Here the unknown is a scalar, but the equation is still scalar here. So this is what we want to solve for. Therefore, we are interested in this, which is the directional derivative of the residual with respect to uh, the directional derivative of the residual in the direction of displacement u. So this is what we want, right? So so we need the directional derivative. So let me just open uh, this week's assignment. So Yeah. So the first question is about linearization of the equilibrium equations, and yeah, even the second question is regarding that, the Newton-Raphson procedure and the directional derivative of the virtual work equation. Now, yeah, so I will not give you the answers, but the concepts I cover will be just enough to solve to answer these assignment questions. So therefore, what I can close this. No, it's not needed. So therefore, what we see is that the directional derivative of, so we need the directional derivative of the virtual work equation or the equilibrium. So we need the directional derivative of the principle of virtual work or the equilibrium equation to get the deformed position, to get the deformed or the current configuration. So this will be, so this iteration. So the iterative scheme is what? The iterative scheme you get by this. So xk you get as, so the iterative scheme will be xk plus 1 is xk plus u, where u satisfies r of xk plus the directional derivative of xk in the direction u is equal to 0. So we know that the directional derivative is linear in u, and this is a known function. This is when you plug in xk, we know this is a scalar. This is probably, so this is a scalar, and this is a vector. This is a row vector. This is a column vector. So the result will be a scalar. So you can find this vector u by solving this equation. So once you solve that, plug it into this. Therefore, you get the current. What is that? You get the current position. Do this iteration, you get the current position. So therefore, we need the directional derivative to get the current configuration of the position. Next, what do we do? So we have to linearize it. So we saw that the third question is, let us linearize or get the directional derivative of the external virtual work done. So what we said is this residual is nothing but the internal virtual work done minus the external virtual, whichever way you define it, right? So if I want to set this del r equal to 0, where is it? Yeah. So this r of I defined r somewhere. Okay, it's external minus internal, right? So let me just put a minus r. So if I want the directional derivative of r at the point xk in the direction u, if I want this is nothing but the directional derivative of the internal virtual work done at the point xk in the direction u minus the directional derivative of the external virtual work done at the point xk in the direction u. Now, can we get this? Can we get this? Yes. So this is the directional derivative of the external virtual work done at the point xk in the direction u is what? It is the directional derivative of this entire thing. Integrated over the volume rho bi del vi dv plus integrated over the surface traction del vi ds. This evaluated at the point xk in the direction u. This should be equal to, yeah, this is what we need to get. Now we know that so again the difficulty here is the limits of the integration depend on the deformed volume. The limits of the integration depend on the deformation. So if you have to take the derivative, this is some kind of a derivative, directional derivative. If you then you have to consider the directional derivative of the deformed volume with respect to the direction u, and you should also need to consider the directional derivative of this surface in the direction u. So this is kind of slightly hard because you need to use some form of Reynolds transport theorem. So instead, what we can do is pull everything back to, so finding the directional derivative in the spatial configuration is difficult. So finding the directional derivative of the virtual work quantities in the spatial configuration is difficult because we have the limits of the integration that depend on the deformation itself. Therefore, use the pullback operation. Therefore, transform the virtual work, both external internal, to the reference configuration. Right, by doing that, by transforming the virtual external and internal virtual work done to the reference configuration, what we get is, so how do we do the transformation? Let's see. So you have the tractions, you have integrated over the volume, tractions dot the delta v ds plus integrated over the volume rho b, this is traction, rho b dot del v dv. So how to transform this? Let us say if you take the, so this is a, suppose this is um, a spatial field. This velocity field is specified in terms of the spatial points, but this actually does not depend on the deformed configuration. So this is nothing but, so this is an arbitrary admissible virtual velocity field. So this is just some, so x is nothing but some chi of a phi of some phi of x, and this function you can write it as some other function of the material point x. So ultimately this depends only on x, not on the deformation gradient. So you can always specify an arbitrary admissible velocity field in terms of the uh, defined over the material configuration. So this can be transformed. What about the tractions? So traction is per unit undeformed volume, and you can use the, so traction is nothing but sigma n, and you can also write this as p n naught, where p is the first Piola-Kirchhoff stress tensor, and n naught is the normal. Sorry, so this is, can write dst as this one. This is just ds naught, right? Tds is a force df. So this force traction is the force per unit deformed area, per unit deformed area, and this we saw it is nothing but t itself is sigma n, and sigma n can be sigma n ds, but ds is the deformed area. You can use the PLR transform and make this as first Piola-Kirchhoff stress tensor n naught, which will give you the t naught. So this will be t naught, which is the traction per unit undeformed volume, undeformed area, and multiplied by the undeformed area, you get this. So the first term, if you call this the first term, let me make first term. So this first term becomes integrated over this S naught. Right? This is dV naught, partial V naught, because everything in the argument has become a material quantity. So you have P n naught dot del v cap, because this is the function in the, and ds naught. Now can we take, so these are quantities defined in the material coordinate system, and this is specified. This is actually T naught, which is specified. So this is equal to integral over this surface T naught dot LV cap ds naught. Now this is specified, does not depend on deformation. This is the input to the problem. This is arbitrary, also does not depend on deformation. And the elemental volume and the initial surface and this elemental volume also independent of deformation. Therefore, if you take the directional derivative of the first term, which is not even a function of the deformation, right? This you say this is the first term. The directional derivative of the first term in the direction u is equal to 0 because it does not even depend on the deformed configuration. This is completely specified. Therefore, the directional derivative of the first term is 0. Now let us look at the second term. So similarly, the second term also is rho p dot del v dv. You take the directional derivative of this in the direction u. What it is? It is directional derivative of, pull everything back to the reference because this volume is dependent on the deformation. So let me take it back to the reference. So rho will become j of x rho naught. B will become some b naught dot. Sorry, it's not j of x rho naught. So I'll come to it. So this is b. B will be some b which is same. B is just specified, and this del v, as I said, it will take the space reference description. Now, if you see rho dv is the mass. It is some infinitesimal mass, and after deformation, it will be. So this is, if suppose initially it is rho naught dv naught. This will be the initial mass. But we have the law of conservation mass says that we cannot have mass loss. So dm should be equal to dm0, which means if dv is equal to j dv naught, rho should be equal to rho naught by j. So in place of rho, you have rho naught by j, and dv is j dv naught, and the directional derivative in the direction u. So this j gets cancelled, and whatever you have inside, rho naught is the initial density of the material that does not depend on the deformation. B is specified, that does not depend on the deformation. Del V cap is an arbitrary admissible velocity field that does not depend on the deformation, and the integration is over a constant volume, so even that does not depend on the deformation. So this is also equal to 0. Therefore, the directional derivative of the external virtual work done in the direction u is always equal to 0. So this assumes that forces are conservative and subjected to a conservative force field. Meaning B and T do not depend on the deformation field. So if you have forces like friction, where the force itself depends on the deformation, and or you have some kind of follower forces. If you have some, if you have a cantilever beam and you have a follower force like this, the force is always perpendicular. Force follows the deformation. In those cases, you cannot say the directional derivative of the external virtual work done in the direction is 0. We can't say this. In general, for this, it's not 0. Okay, so when subjected to so the linearization of del W external is equal to 0 when we have a conservative force field. Now next, let us look at the linearization of the internal virtual work done. Okay, so this is going to be somewhat lengthy because the entire in the entire week that is what was covered. So here we want to linearize. We want to linearize this. So we need the directional derivative of the internal virtual work done in the direction u. What it is the directional derivative of integrated over the volume sigma double dot product with the virtual rate of deformation tensor and integrated over the entire volume in the direction u. Now we have to be careful, right? Now we have to be careful. So what does sigma depend on? Sigma is a function only of the, this depends only on the deformation field. Let us say x. And the virtual rate of deformation tensor. So this is the actual stress field. The actual stress field. Whereas this is the virtual velocity field. So this virtual rate of deformation tensor depends only on the virtual velocity field, not on the actual deformation. This you are specifying. So this virtual rate of deformation tensor is virtual rate of deformation tensor does not depend on actual deformation. This we are specifying, right? So there's no dependence of this on the actual deformation. Okay, very good. Now, so first step. So let's say problem. So this is problem 4. First, we have to linearize it. So express it in the material description, material or reference description. So we have already spent an entire week on that. So we know that. So we spent a week on this verb conjugacy. Where we said the internal virtual work done is equal to sigma inner product with del d dv is equal to what? This is equal to integrated over the reference volume p double dot del f dot dv dv naught. This is also equal to integrated over the reference volume s double dot del e dot dv naught. And we also had other referential descriptions of the internal virtual work done. So let us start with this, right? So the expression for internal virtual work, expression for the directional derivative of the internal virtual work done is d integral over the reference volume s double dot the virtual Green-Lagrange strain tensor dv naught and in the direction u. Now you can express, this volume is independent of the deformation, so you can take the directional derivative inside. So it's integrated over the volume d s double dot del e dot dv naught. Sorry, this in the direction u dv naught. Now we can use the product rule. So so this you can write in initial notation as d sij del epsilon dot ij, sorry, del e dot ij in the direction u dv naught. But what is this? This now we can use the product rule. It's just the product of two scalars. So it is integral over b naught d sij in the direction u, delta epsilon dot delta E dot ij. So this is the rate of green Lagrange train dv naught plus integral. Now the second term. Now keep Sij constant and take the directional derivative of the virtual rate of the virtual material time derivative of the green Lagrange train tensor. Sorry, the material time derivative of the virtual green Lagrange train in the direction u dv naught. Right. So this is the directional derivative of the internal virtual derivative. So this is the directional derivative of the internal virtual work done in the direction u, where u is some correction, u is some displacement. Okay, so now what is it a function of? Again, remember, so the internal virtual work, it is a function of both the deformation phi as well as the virtual velocity field delta v. And individually, if you look at this, the term S is a function only of the deformation field. Del E depends only on the virtual velocity field. And yeah, these are the terms that mainly appear. Now we look at, so this is fine. So this is the directional derivative. This is an expression for the directional derivative of the internal virtual work in the referential coordinates. So it is always easier to represent these in the referential coordinates because the limits of integration do not depend on the deformation, which is our intended, which is the solution that we want to find out. Now, next thing. So now we look at the result. So what is the number? Went to 4. Now we look at the problem. So this is an important result, which we'll be using again and again. Oh, okay, it's not required. So first, let us look at this term by term. Okay, so okay, so let us start with this one. Okay, so let us look at the term integral over the volume, the directional derivative of the first second Piola-Kirchhoff tensor Sij in the direction u, and here you have a del Eij dot dv naught. Now we will show. Let us show that this is equal to. Let me get the expression. This is equal to. So this can be equal to integral over the volume sorry. So this is equal to the directional derivative of E in the direction U, double dot product with the constitutive material constitutivity, material elasticity tensor C on or let me do one thing. This equal to, you can say this is the virtual velocity field, the virtual green Lagrange train rate field contracted with C dE the directional derivative of E in the direction U. So be careful. So this del E dot is a virtual green Lagrange train rate. And this does not depend on what? It does not depend on the actual deformation phi. And this is the actual there's a dv naught, of course. There's an actual directional derivative of, sorry, it's actually the directional derivative of, this is the directional derivative of the actual green Lagrange strain tensor. And this depends only on phi and not on del v. So this is the actual solution. So this can depend only on you, and it is irrespective of whatever virtual field we are assuming, right? So this depends only on the actual green Lagrange. Yeah, this depends only on the actual motion, actual deformation. So let us show this. So if you do this, so this is simple. Use the definition of the material elasticity tensor. What is it? D S in the direction U is equal to some constant acting on the directional derivative of the green Lagrange strain tensor in the direction U. So this is how we started off with, right? So this, in the hyperelasticity section, we saw that the material elasticity tensor is defined as that operator which relates the uh, second PLR which, so this is a fourth order tensor. This is a fourth order tensor that relates the so this fourth order tensor takes in the directional derivative of the green Lagrange strain, and it returns the directional derivative of the second PLR Kirchhoff's test. So this is the definition of C. So directly plug it into this. So what this means? This means that d S ij of U in component form, this is what? So this is a second order tensor. This is a second order tensor. So what it relates is a fourth order tensor. Cij KL d EKL in the direction U. This is straightforward. This is very straightforward. So this term, the directional derivative of, sorry, the first term, right? The directional derivative dSu double dot with d epsilon dE dot del E dot dV naught is equal to just use the definition of the elasticity tensor. We get integral over volume. So this is d Sij in the direction U del E dot ij dV naught. This is nothing but integral over the volume V naught. D Sij is nothing but d Cij KL Sorry. So this definition, the directional derivative of Saj, the definition itself isCijkl, the directional derivative of EKL in the direction U, and you have a del E dot Ij dv naught. Now this you can write it as C double dot dE in the direction U, and this is multiplying with ijth component of this. So this you can bring it to the other side. So it is del E dot double dot dv naught. Okay, so this is fine. So this directly follows from the definition. Next, what do we do? So next you look at a result, right? So this is 5, then result. The material time derivative of a tensor of something, of a tensor vector of the material time derivative of a quantity, right? Of any quantity is nothing but its directional derivative in the direction of the velocity. The velocity at that point. So this is a very useful result. We'll see how it is coming up. Right? So suppose we'll just take E. So we have the material time derivative of the virtual green Lagrange train E. So this is nothing but the material time derivative of del E. But what is the material time derivative? Material time derivative is keeping the keeping the material point constant. It is keeping the material point constant. So this is constant. This is fixed. So the material point is kept fixed, and we see how the field actually varies at that point. So this you can write it as del E of. So you can, in the material description, E is anyway a material tensor, so it is nothing but del E of some x plus x comma t plus delta t minus del E of x comma t divided by delta t. The limit delta t goes to 0. So this is the definition of the material time derivative. Now, yeah, in the process you're just keeping x fixed. So our objective is to show that this is nothing but the directional derivative of E in the direction of the velocity field. So suppose now take this quantity, the directional derivative of E at any point in the direction of the velocity. Now consider a displacement just a minute. Yeah, consider displacement U is equal to V delta t. Right, consider displacement, use v delta t. So, and this displacement, you can think of it as a perturbation onto x. So E is a function of x. So what is E of x plus u? It is the E of x plus um, plus the directional derivative of E at the point x in the direction u. But this u is now v delta t. So this is E of x plus dE x u is v delta t. And we know that the directional derivative and plus higher order terms, plus some higher order terms. And we know that the directional derivative is linear in the direction. So E of the E you find out from x plus v delta t is nothing but E of this deformation plus dE plus you have a delta t dE what it is, you get plus dE at this point x in the direction v plus the higher order terms. So these terms are all of the order delta t square times something. Right now, now take the difference. So it is say E of x plus vt minus v delta t. Sorry, E of x plus v delta t minus E of x uh, divided by delta t is equal to d e x v plus delta t. One delta t gets cancelled, so delta t times something else. Now take the limit. Delta t tends to 0. So this is E of this x plus v delta t minus E of x divided by delta t, and this is dEx v, and these terms vanish. Now look at this, what it is. So this part, if you see, this is E of x plus v delta t, but x plus v delta t is nothing but but v itself is dx by dt. So this you can write, which means x plus v delta t is nothing but x plus dx by dt delta t. This you can write it as some roughly it is x of x comma t plus delta t, right? So you're keeping the same material point fixed. So it's like, is look at this. X is a function of both x and t, and if you use the Taylor series, you get x is x of sorry, x of x comma t plus delta t is what it is, x of x comma t plus by dt, keeping x fixed, delta t plus some higher order terms. But this itself is v, and therefore this term is nothing but x plus v delta t is nothing but x of and plus terms higher order in delta t. So this is just this x of x plus delta t. So this you can write it as x. So this you can write it as limit delta t tends to 0. It is E of x plus bt. X plus bt is x of x plus t plus delta t. So it is some E of x comma t plus delta t. And what is this? This is E of x, and x itself is a function of x and t minus e of x comma t divided by delta t plus higher order terms, those will vanish because you're taking the limit delta t tends to 0. This is equal to the directional derivative of e at the point x in the direction v. So, but what we have on the left hand side is the material time derivative. So this is e dot. So e dot is nothing but directional derivative of e in the direction. And there is nothing special about the e we assume. So e, although I started off with the green Lagrange tensor, you can also put some t. And nowhere I have used the definition of e here, right? Okay, so let me save it. There is this issue. So nowhere I have used the definition of this. I'll close and open it again. Okay, yeah, anyway, so nowhere I have used the definition of E as half F transpose F minus I. So this holds for any tensor. So the directional getting stuck. Okay, this is all gone fine. So yeah, so what I said here was consider displacement u as v delta t, and so and say find the directional derivative. So you get e of x plus v delta t is nothing but e of x plus the directional derivative of e at the point x in the direction v delta t, and plus the higher order terms. And we said that the directional derivative is linear in the direction. So this is e x plus e x in the direction v. Delta t comes out plus delta t square times other terms. But what about this? So this is e of x plus v delta t minus e of x is equal to delta t times the directional derivative of e at the point x in the direction v plus delta t square times some terms. But this itself, we said it is this itself, x plus v delta t is nothing but some x of x comma t plus delta t minus some higher order terms. So this you can write it as e of x comma t plus delta t. So in delta, this is the change in position x. So why is this so? This is because v is equal to dx by dt. Right? The material time derivative of the position with respect to time is v. So x plus dx by dt is some the new configuration, right? It's a different configuration at time t plus delta t minus some higher order terms. So this is x e of x comma t plus delta t plus some higher order terms minus e of x. This is equal to delta t times the directional derivative of e in the direction. I don't need to put the this one anymore. In the direction v plus delta t square. So this delta these terms can be clubbed together. Divide throughout by delta t and take the limit delta t tends to 0. So this means e of x comma t plus delta t minus e of x comma t divided by delta t is equal to, so there is a delta t here that goes away. You get the directional derivative of e of x comma t in the direction v plus delta t times something. And here you apply the limit delta t tends to 0. So this terms will vanish, and this is nothing but the material time derivative of E. The material time derivative of E is nothing but the directional derivative of E in the direction of the velocity field. So again, I can drop the dependence in the direction of the velocity field. But this is nothing special. There's nothing special about this tensor E. I didn't use the definition anywhere. Therefore, the material time derivative of any tensor is the directional derivative of the tensor in the direction of its velocity, in the direction of the velocity. Now, if you go back to the expression we had, this expression, we have a del E dot. So what if E dot is the green Lagrange strain rate that is equal to the directional derivative of E in the direction of the velocity field. What is del E dot? Del E dot is the virtual green Lagrange strain rate. That is the directional derivative of, there's no del here because remember del is not it's not a differential operator, although it works like a differential operator most of the time, but it's actually a difference, right? It is some kind of a difference. So that is what is arising from del V, right? So this have to be careful. So the green Lagrange strain rate, the material time derivative of the green Lagrange strain rate, virtual green Lagrange strain rate, is the directional derivative of the green Lagrange strain rate in the direction of the virtual velocity field. So this is a result. Now plug this into this expression. Plug it into this expression. This expression. So here in place of del E dot, you can put that. So what we get is integral. On the left hand side, we have d, the directional derivative of the second Piola-Kirchhoff stress tensor in the direction u, double dot with del E dot dv is equal to integral with respect to v. First one was del E dot, so I can write it as so I'll repeat it, del E dot double dot with c double dot with E in the direction u dv naught. It's all in the reference configuration v naught. Now this is nothing but this I can replace, so I get a v naught, the directional derivative of E in the direction del v double dot with c double dot with del there's no del. This is d. This is de. Let me. The definition of ds is cde. So this is not a del. This is a d. de in the direction u. So what we can see, so we know that the directional derivative of E is linear in this, the directional derivative of E is linear in this, and you see the C symmetric. This is symmetric. E is symmetric. Therefore, this entire quantity is symmetric with respect to del V and U. So what is del V? Del V is an arbitrary virtual velocity field that we are imposing, and U is the some perturbation. U is some adjustment to the displacement vector. U is then some adjustment to the configuration. It is some displacement. So what we find is that this expression is symmetric in both del V and U. So this is an observation. So this expression is symmetric. Basically, it means if we swap U and del V, there's no change. Expression is symmetric in del V and U. Okay, so we have come to this point. This is result 6, but we left out one term here. Right? This is the first term. We also had another term, which is so this is one term of the product rule. The other term, what is the other term? It is integral over the volume. S remains as it is. S remains as it is. Double dot d e the direction. Sorry. D del e. Del e dot in the direction u. dv naught. Right. So this let us see what this is. So we have to see how this comes. So S is the second Piola-Kirchhoff stress tensor. E is the Green-Lagrange strain rate associated with the velocity field del v, and U is the correction displacement, which we are looking at. Now, we can do this. So we have to find this quantity, right? This is not symmetric. You see, this quantity is not symmetric in U and del V. So del V is somehow inside this del E dot, and we don't know how this works. So let us see. But we know that del E does not depend on the thing that we know is del E dot does not depend on V. Del E dot does not depend on U. U is a perturbation applied to the configuration, whereas del E dot is not. Del E dot has got nothing to do with that. Del E dot is coming purely from the imposed velocity field. So let us look at this quantity d of L dot in the direction u. So what is this? This is nothing but let us see. So this is the first thing that we need to see is what is del E dot. So let the directional derivative be. But what is del E dot? It is the Green-Lagrange strain rate associated with the velocity field v. Okay, so velocity field del v. So this depends only on del v. But you know that E is something like F transpose F minus I, half of F transpose F minus I. So by imposing the velocity field, V, will F get affected? Is there an F associated with this del V? So we have to see that. So to see that, let us say, so by imposing the velocity field, what happens? The deformation tensor, the deformation map x of x comma t, right? So this is nothing but say xi of x1, x2, x3, t. So when I say I'm imposing this del v, what it means is I'm going to add a del v del t to this. Okay, So by imposing this, I mean, so we have this. So by imposing this, it means I'm putting this. This becomes x plus del v times some small. Hmm, okay, so let us see. So it means I'm imposing a small. Uh, Let us see. So so what it means is that when I impose this velocity field, what happens is the deformation. So let me put it this way. So we have x as a deformation. So I'm imposing some virtual velocity field means after a time delta t, what happens? X of x comma t plus delta t will be x of x comma uh, t plus this del v times delta t. That is what it means. So this is the solution. X is the solution, but I'm imposing some field. Say, right? I'm imposing this velocity field del v. So what happens after a time delta t? By telling that I'm imposing a velocity field, it means that after an infinitesimal time delta t, uh, this x will be x of uh, this actual x of x plus x comma t plus some del v times t. Now let's take a gradient on both the sides. So for this, if we take a gradient, we see that f of comma t plus delta t will be f. So I'm just taking a gradient f of x comma t plus the this is a gradient with respect to the original coordinates, right? Del v del t. Now take it to the other. Now take this delta t to the other side. So you get f dot. Right. So this is f of t plus delta t minus f of t divided by delta t. Take the limit. This is equal to some gradient of the virtual velocity field. So, but if you take a spatial gradient, f itself does not depend on delta v. So you see, f does not depend on delta v, but f depends on the mapping phi, and therefore its directional derivative u will affect it. However, f dot, if you see, f dot is depending on delta v only. So this I can say this is the rate of deformation. This is the deformation gradient, the rate of time derivative of the deformation gradient that depends on delta v. So that is f dot is equal to gradient of delta v. So this I can call it as this is arising only from the imposed velocity field. So this is the component of the deformation gradient that is coming. So you see one component is this f of x has itself before imposing that velocity field, it has the original deformation gradient which comes from the deformation, actual deformation, and it also has a component coming from the virtual velocity field imposed. So this is the virtual. This is the material time derivative of. So this is the virtual material time derivative of f. So this is the virtual f dot. Now, if you so f dot depends on del v. So this have these two observations. F does not depend on del v, but f dot depends on del v. So therefore, there's an associated del f dot. Right. So by imposing this, by imposing a virtual velocity field, we will not affect the deformation gradient at that instant. We will affect the deformation gradient in the future, but we will not affect the deformation gradient at that instant. But we will affect the deformation gradient rate at that instant. So the deformation gradient rate has a virtual component, which is virtual deformation gradient rate. Now, if you see what E dot is, what is E? E is half of F transpose F minus I. What is E dot? E dot is the material time derivative of the green Lagrange strain tensor. So this is half of, use the chain rule, it is F dot transpose F plus F transpose F dot minus I dot is 0. I is a constant, right? So this is okay. Now what should we do? So, but this is the green Lagrange strain rate. Green Lagrange strain rate. This is the total green Lagrange strain rate. But what is the component that is coming from? What is the component coming from the virtual velocity field? Del V. So that is that we say del E dot, that comes from. So F is unaffected by del V. So F will remain F, but F dot is associated with del V. There is an F dot which is the material gradient of del V. So there is del E dot is del F dot transpose F plus F transpose del F dot. Okay, so we got an expression for this in terms of F. What is the next step? We actually wanted to simplify this. So we want a derivative, we want a directional derivative of this del E dot in the direction U. So what is it? The directional derivative of del E dot in the direction U is nothing but the directional derivative of del F dot transpose F plus F transpose del F dot in the direction U. Remember, del F dot is coming from del V and does not depend on what? It does not depend on um, it does not depend on the configuration or U. So the directional derivative with respect to U, where U is a perturbation to the configuration, will not affect del F dot, because del F dot is coming from the imposed velocity field del V as the gradient of material gradient of del V. Therefore, this, if you take this, apply the chain rule for directional derivative. So this is equal to del F dot transpose df in the direction U plus df transpose in the direction U acting on del F dot. Right? So, okay. Yeah, so what is F in the direction? So this is this we already got. This is F dot. This is the gradient, the material gradient of V. Sorry, not V. Del V transpose. What is df in the direction U? This is simple. F is gradient of x, but this so what is the gradient of x plus U is what? This gradient of x plus gradient of U. But by definition, gradient f of x plus u is f of x plus df of x in the direction u plus higher order terms, which means the directional derivative of f in the direction u is nothing but grad u. So this is nothing but grad u, right? This is nothing but grad u. Plus, what about this? So the directional derivative of this is f transpose is nothing but grad u transpose. So the transpose can be interchanged. So you just get a grad u transpose. And what is del f dot? Del f dot is the material gradient. All these are material gradients. Yeah. So these are all material gradients. Material gradient of del v. Right. So look at this expression. It has a del v transpose del u plus del u transpose del v. What is this? This is the symmetric part of uh, del v transpose del u. Right. Sorry, this is not the symmetric part. This is 2 times the symmetric part. Because if you take this and you take a transpose of this, you get del u transpose del v transpose, which is the second term. So this is two times the symmetric part of this thing. So actually there is a problem. So there is a half here that got missed. So everywhere we have a half. So there's a half. There is a half. There is a half. And this 2 by 2 gets cancelled. So this, now substitute this in this expression. What we started off with something like this s colon this. So s colon the directional derivative of the virtual Green-Lagrange strain rate in the direction u dv naught is equal to integral over v naught s contracted with what did we just get here? We to be equal to symmetric part of del dot v transposed. It's not dot. This is the material gradient, right? It's not dot. So therefore, the linearization of the internal virtual work, linearization of the internal virtual work in the direction u is what? This is one term of the product rule, and we had another term. So if you see, this is equal to the first term that we got was integrated over u. One was the directional derivative of E in the direction del V double dot the material elasticity tensor double dot the directional derivative of E in the direction U dV naught plus we had this thing integral over V naught S double dot the symmetric part of this, which is del naught V transpose del naught U plus del naught U transpose del naught V. dV naught. So this is the expression for the internal virtual work, directional derivative of the internal virtual work with respect to U. And note, it is symmetric. Symmetric in U and del V. Right? So S is a symmetric tensor. So what it means is So remember, S depends on the configuration. C depends on the configuration. E depends on the configuration. But these the first term is linear in both that increment. You have a u. So this is linear in the directional derivative of E in the direction u is linear in u. And the directional derivative. So this entire expression has to be linear in u by definition. But it is also linear in delta v. So this one is linear in delta v. And delta v does not appear anywhere else. Although C depends on the configuration, but not on u. In the second term, S depends only on the configuration, not on u, nor on delta v. So S is the actual second Piola-Kirchhoff stress that is already arrested. So when we have an equilibrium configuration, we have a certain S, and u is a correction. S does not depend on u, and delta v is a virtual velocity field that we are imposing. So S does not depend on that also. So we see if we interchange v and u in this full expression, it will commute. There is no, it will make no difference. Therefore, this expression for internal virtual work is symmetric in u and delta v. Okay, so let me see you have 10 minutes left. So let me see the assignment if we have any other questions that are not answered. So the Eulerian linearized internal virtual work can be, okay, this I'll do. It's convenient to perform, yeah, this I have covered. Linearization of the internal virtual work can be carried out easily using the material form, spatial form. Okay, yeah, we have done that. So yeah, remember it's easily. And I said in the material form, the limits are independent of the deformation, whereas in the spatial form, limits also depend on the deformation. So the limits should also get into the linearization. So that's not easy. Then true or false, the virtual velocities are function of the configuration. Of course, you know the answer. I've repeated it multiple times in the session. The pullback of the virtual rate of deformation tensor gives the directional derivative of the Green-Lagrange strain tensor in the direction of the virtual velocity. Yeah, so this has to be looked at. And the last one, the symmetry of the tangent stiffness matrix is because the virtual work equation is symmetric in the virtual velocity and displacement. Yeah, this we have already seen. The virtual internal work is symmetric in both the virtual velocity and displacement. So yeah, tangent stiffness is nothing but whatever is multiplying u. So whatever is multiplying u is the tangent stiffness, and you see that is actually symmetric. So you can figure out. Okay, yeah, that you can figure out. Now we'll look at, so this is entirely in the material configuration. Right? This is all in the material. This is all purely material description. Can we get a spatial description? We need a spatial description. So this is, I forgot the question number. This is 7. Let's go to 8. Spatial description of linearization of the internal virtual work. So recall that this is external, this relational derivative of the external virtual work done with respect to any displacement is 0, whether it is description only changes. So something that is 0 cannot become non-zero. So whether it is material description or spatial description, this will be 0. Now look at these terms. Right? Look at the yeah, look at the terms in the so this is what we had. Right? This is the full del W int. I'll rewrite it. So del W internal is nothing but this thing. So I'll copy paste it there just to save some time. I'll bring it down, no problem. Yeah, this is the expression for the internal virtual work done. Now look at the first term, right? So next we want to get a spatial description. So yeah, so we know that S. Okay, so we want to get a spatial description. Okay, so S is equal to, so this directional derivative of S in the direction U is equal to C double colon the directional derivative of E in the direction U. But U can be anything. If I choose U to be the velocity vector, choose U to be the velocity vector, then I get the directional derivative of S in the direction of velocity is equal to C double dot directional derivative of E in the direction of velocity. But this is, we just proved that for any tensor, the directional derivative in the direction of velocity is S dot. S dot is equal to, we get C double dot E dot. Okay, so this is fine. Now, this is okay. Next. So this in the what happened? So this means Sij dot is equal to Cijkl EKL dot. The Cijkl is not a constant. It can depend on the deformed configuration. It depends on the deformation. That is okay. That we know. Now, can we push? Can we push forward Sij? Yes, we can do that. So how do we do that? We can say so FIP FJQ Sij dot. What is this? This is nothing but the ijth component of Fs F transpose. But what is Fs F transpose? This is nothing but J F inverse transpose. Yeah, this is J J times J inverse Fs transpose Ij. So you recall what this is. Fs is the Piola-Kirchhoff. This is the first Piola-Kirchhoff stress tensor. Sorry. Yeah, and what is J inverse P F transpose? This entire thing is the sigma. So FIP FJQ S dot IJ is the sorry, this is there is a dot here, so it's not sigma. It's not sigma. Sorry. So this is S dot. We can't do much. So we want to pull it, push forward this. But if you see S dot, S is J F inverse sigma F inverse transpose. S dot is J dot F inverse sigma F inverse. Okay, but okay, let me do one thing. So this if you look back at the old notes, sir would have shown that this is the Truesdale stress rate. So if you recall, you take we define something called the Truesdale stress rate. So that that is nothing but the Piola transform of is J inverse of the push push forward of, so yeah, push forward of S dot, right? So sorry, so just a minute. So this I'll get the expression right. So mm, okay, so we have this. Okay, one minute. Let me actually check. So this is what we have. We don't really have S dot appearing anywhere, right? So that's not required. So this we don't need to push forward S dot. Right? I'm sorry about this. We don't need to push forward S dot. We don't really need to push forward S dot. What are the terms appearing here? We have a C del E D E del V and this one. Now let us instead push forward these things, right? So uh, let us take U as some sorry, use the correction. So U as some V delta T, right? So this means, so remember V is not virtual here. U is a correction. So correction, if you take infinitesimal times, you can say it U is some velocity times. So let me not use this delta. Let me use this delta T. Okay. So what happens to the first term? Let us call this the first term, and let us call this the second term. Okay, one more thing. There's a del here. Sorry about that. So the first term becomes integral. So first term is dE in the direction del V double dot. So this is first term integrated over the volume. Double dot dE in the direction. This is the actual velocity del T dV naught. So we know this is just E dot. So this is del E dot C double dot with, again this delta T can come out. So bring this delta T out. So you get a dE in the direction. So this is capital D. What I'm doing? It's capital directional derivative of E in the direction V delta T. So this is nothing but E dot. This is a real velocity. This is virtual velocity. So it's a correction velocity. Okay. So this is the case. Now look at E dot. What is E dot? E dot is half of F transpose F minus identity, the whole dot. So this we did everything. We did this is F dot transpose F plus F transpose F dot. We have done it multiple times. And this is So again, use the relation F dot is equal to LF. Right? We have used this multiple times. So this becomes half of LF transpose F plus, let me use small l, F transpose LF. So this becomes half of F transpose L transpose plus L F, and this is nothing but F transpose L, sorry, not del, L plus L transpose by 2 is D F. So in place of E dot, substitute this, we get the first term is delta D integral over V naught. It is F transpose D F double dot with C double dot with E dot. E dot is again, okay, this is delta D, right? This is delta F transpose. So E dot is F transpose DF. Del E dot is F transpose del DF, because del V will not affect F. This del E del D F double dot with C double dot with F transpose F PV naught. Now look at this expression. What we have, it is F transpose. So this is equal to integral over the volume F transpose. Get rid of the delta T. It's not important. F transpose del D F Ij Cijkl is the material elasticity tensor multiplied with F transpose DFKL. So first one can write it as V naught F transpose Ij, F transpose not Ij, F transpose IP del D PQ F QJ Cijkl. Remember the net result has to be a scalar, and again this is F transpose KP, not P. PQ is already used. KR D RS F SL. This entire thing dV naught. So this is integral over the volume. F transpose IP is FPI, and FPI FQJ. So F transpose KR is FRK, and this is FSL, and this is CIJKL. And what else we have? Del P PQ D RS dV naught. But what is this? So this is the this is what? This is the push forward of CIGKL. And in the hyperelasticity chapter, we also defined the spatial elasticity tensor. Which is italic C, is J inverse times the push forward of the material elasticity tensor C. Right. So this this is what related sigma dot to D dot. And this was the relationship. So the spatial elasticity tensor, which relates sigma dot to D dot, was J inverse times push forward of the material elasticity. So this is the push forward of material this thing. So this is P star of C. So this I can write this as J times C. Okay, so this is integrated over volume. J times what are the components? IJKL. IJKL is getting multiplied with this, so it is PQRS. So J C PQRS. These are the PQRS components of spatial elasticity tensor C multiplied with del dpq drs dv naught. So del D is one virtual velocity, virtual rate of deformation tensor. D is the actual rate of deformation tensor, and there's a delta T somewhere sitting outside. So this is nothing but so again you have a J dv naught. dv naught is just so this is integral V. So this is del D C D dv. Again, this is also symmetric in del D and D, where del D comes from del V and D comes from Q. So yeah, we are out of time. So maybe this is a good place to stop. So similarly, you can also transform the other case. So S, you can write it as J times J inverse times sorry, S, you can write it as so if S is F inverse P, which is F inverse J sigma F inverse transpose. So S is basically the scaled pullback of sigma, and then this part also. So this gradient, the gradient with respect to material coordinates can be written as some. So this is nothing but dou by dou capital Xj of something, and it is dou by 2 small x multiplied with dou small x by 2 capital X. So if I put some I, J, something like this. So this is like the gradient with respect to the material coordinates is gradient with respect to the spatial and you have an F transpose multiplying it. F transpose. So this you can check. This you can check. So it's F transpose gradient and substitute all that into this. So this also turns out to be something simpler. So you can get rid of the material, and this will actually scale it back to sigma. You get a sigma double dot grad V, the symmetrization of grad V and this thing. So the virtual work, the directional derivative of the internal virtual work expression will also be symmetric with respect to U and del V. Also in the spatial description, it has to be. If it is symmetric in the material description, it has got to be symmetric in the spatial description as well. So maybe I'll stop here, and thanks for attending. I'll stop the recording here.
Hello Naresh, I have some
Yes.
doubt.
Yes, sure.
In lecture 29, no, sir solved two problems. So
Okay.
in that last problem, can we solve now? Because I was solving that,
Okay.
but
So
I
like
am not getting that proper answer.
okay. Lecture 29 is this one, is it? Okay.
Yes,
I'll
mu
open the
gain.
lecture notes, maybe. That's easier.
Okay. And also, I sent you a mail. Have you seen that?
Yeah, I've seen that. I looked at it. It was mostly correct. So it was some.
Yeah.
I thought I didn't have my writing pad on at that time when I checked it. So the
Okay.
answers are mostly correct. It is because somewhere you missed out some small divided by 3 or something. So that caused the issues. So
Okay.
I'll mark it and then I'll send it back. Yeah, I didn't have the
Okay.
time for
Okay.
it, but I'll
Fine.
do it. Yeah.
Okay.
So conceptually, there was no big issue in that in your answers. So they were
Okay.
fine. And one answer was dependent on the other. So that.
Okay.
Okay. So Neo-Hookean.
Yes. Yes.
Oh, which
We
is
will
this?
see
Okay, this one, right?
first
Second
problem.
problem.
Yes. Yeah, we will see first problem also because in last step, no, I think sir has not
Ah,
included that mu while
oh, okay.
calculating the pressure.
Okay. So let me. Okay, let me
Yeah.
do this. So consider the simple under simple shear. is a scalar. Using the Neo-Hookean material model, determine the pressure P. Okay. Yeah, mu should not get into the expression for pressure. I'll tell you why. So this mapping is x1 is equal to capital X1 plus AX2.
Yes.
And x2 is equal to capital X2. Okay. Other two directions, no, small x3 is equal to x3. Okay. Now we'll find out f. F is,
Yes.
so it is 1, 0, 0. So x1, no, sorry, 1,
A1 A will become
0.
0.
Yeah, 1, A0. Then it is 0, 1, 0, 0, 0, 1.
Yes.
Okay. So C will be F transpose F, which is 1, A0, 0, 1, 0, 0, 0, 1, multiplying 1, A0.
We required B, no?
Sorry, we
We
require
require B. That is
okay.
left.
Okay, yeah. Okay, let me do the that way.
Yeah.
So this will be 0 and this will be okay. So this is 1 plus A square. The second term will be 1A, and third will be 0, and this will be 0. This will be symmetric, so A, and this will be 1, 0, 1. Yeah, this will be 1, and this will be 0, 0, 0. And last one will be, I think, 0, 0, 1. So this is
Yeah, 0, 0, 1.
so B, yeah, B will be this. Okay, so we have B. Then, so what is the Neo-Hookean model? I don't remember that. So
Sigma
we
is
have it.
mu by lambda, mu by J, I think. Yeah.
Okay, mu by J, B minus I. Okay.
Yeah.
So we have sigma is mu by J to
B
B
minus
minus I plus
plus
lambda
ln J by I.
Ji. Okay, so this is fine. So B minus I will be A square A0, A0, 0, 0, 0, 0, 0. So okay, so yeah, so the question is to calculate the pressure P, right? So before even you get to that point, let's see. Pressure P is 1 by 3 sigma kk. It's the of sigma by 3.
Yeah.
Yeah, so this is keep mu by j. Trace is linear, so it is trace of b minus trace of I, which is 3, plus lambda into, this will not change, logarithm of j by j into trace of I, which is 3.
That J is there actually,
So
Naresh. Lambda ln J by
okay,
J is there. I think J is not there, no? Can you
is it not
confirm
there?
that
Okay.
equation? Yeah. Previously, when we derive, I think that J is not there.
Oh,
In
okay.
last, yeah. Also in last example, you can see that J is not there, I think. J is there?
J is there.
Okay, J is there, okay.
It looks like j is actually there.
Okay, I think in the, is there any difference between this and the video lecture? Because in video, I think J is not there.
Oh, okay. I have to
Can you
check.
confirm that, please? Yeah.
Yeah. This is the video lecture.
Yes.
Okay, yeah. It
Yeah,
doesn't
J
have
is
the
not
J here.
there.
Okay, so
So which is now
this.
correct?
Okay, then we have to see the derivation where he derived it. So let's see
Yeah.
that. So it should be somewhere before this.
Yes.
Compressible Neo-Hookean hyperelastic. Okay, yeah, this is the one. So this is the spatial description. Okay. So it is 2 times.
So sigma is above, I think, not here. Above that, yes, direct.
Yeah.
Yeah, below. Yeah, below it was.
Yeah, this is differentiation. Then S is there, fine. So in
Yeah,
S there is
sigma.
no J, which means I
Yeah.
think there should be there should be a J in the denominator. Yeah, because if S is like this, sigma has a J in the denominator, right? So it's mu by J, B minus I plus lambda log J by J.
J is there, no?
Yeah, J is there.
Okay, that's why maybe.
Oh,
Yeah,
maybe
we
that's
can
the
solve that.
difference. Okay. Okay, so this is what is trace of B? Trace of B is 1 plus A square plus 1, which is mu by J, A square plus 3. So A square plus 3 minus 3 is just A square plus lambda log J by J 3. So J is actually, J is 1. Therefore, this will not contribute. So it's only mu A square. So pressure is just mu A square.
Yeah, but okay. U square,
Is
no?
that okay? It's mu A
But
square. What does he have?
A square, I think. A square by 3.
Is there a value for mu?
No,
Okay,
not
there's no mu.
mentioned.
Now, as A tends to 0, we get what is called pure shear. No, it cannot be. If A tends to 0, there's no deformation, right? It's just 1, 1, 1. It's not. Yeah, why did he do that? It's mu by J is fine. B minus I is okay. B trace of B, we got it as 3 plus A square. That's also
Yeah.
okay. Minus 3 is just A square. Mu by J is, so J is 1. It's mu A square.
Yeah, mu square by 3 actually it should be.
Okay. There is a 1 by 3 that I missed.
Yes.
It's mu A square by 3. Yeah, okay. You said he has missed out a mu here, right? That's
Yeah,
correct. Yeah. It should be mu A square by 3.
yeah. And please
Okay.
solve last one also because I'm getting
Yeah,
different answer.
I will do that. So consider deformation given by this. Consider Neo-Weekend material strain energy discuss. Okay, 3. Okay, that's fine. Find Jacobian of the deformation first invariant. So let me just copy paste this.
Okay.
I don't want to write it.
Yes.
So this. So this is. So let's find F first. F is grad x1. So it is 4 minus x2
Yes.
minus 5 minus x1, and then it does not depend on x3. And x2 is
Mm.
2x1 plus 1x2, 0. And x3 does not depend on both. Okay, did they give a point? They gave a point as 1 comma 1 comma 1.
Yes.
So it is 3 comma minus 6 comma 0, 2 1 0 0 1. Okay. So Jacobian they're asking. So Jacobian is 3 minus 2 into minus. So it is 12. So it is 15. So is it matching? Yeah, Jacobian is matching.
Yes.
Then first invariant of the Cauchy stress tensor. Yes. So we need B, which is FF transpose. And FF transpose is 3 minus 6 0 2 1 0 0 0 1. We have 3 minus 6 0 2 1 0 0 0 1. So it is 3 square plus 2 square, which is 13. Then minus 18 plus 2 is minus 60. Then 0. Then this and then 0, 0, 1. So BB transpose. This is B. So sigma is defined as that expression lambda. Sorry, this is mu by J I minus B, right? What is it? B minus I plus lambda. Lambda log J by J.
Naresh, I think you have done one mistake.
Okay.
F is 3. F matrix is our 3 minus 6 0, no? So you have taken the transpose of it.
Oh, sorry. Again, I have done C. Yeah. It's
Yeah.
wrong. It is FF transpose, right? So this is
Yes.
wrong. Sorry. So B is 3 minus 6 0 2 1 0 0 0 1. 3 minus 6 0 2 1 0 0 0 1.
Yes.
And multiplied by F transpose 3 minus 6 0 2 1 0 0 0 1. And this is 3 square. This first term anyway doesn't matter. First term has to be okay. No, so it changes. So 3 square 9 plus 36 45. Then it is 6 minus 6 0.
0.
Right, it is 6 minus then 0. So again this is 0 0. So second one is 2 square plus 1 5. Then 0 0. Then 1.
Yes.
Yes, so it is diagonal. That's very good. Okay, then we have sigma is mu by J B minus I plus lambda log J by J into I. So here it is mu J we need to find. J is 15. So it is mu by 15. B minus I is 44 0 0 0 4 0 0 0 0 plus lambda log 15 by 15. It's log 15 by 15 I. So mu and lambda, I think he gave some values. Mu is 2, lambda is 3. So it is 2 by 15 into 44 0 0 0 4 0 0 0 0 plus 3 by 15 is 1 by 5. This log 15 by 15 into 1 0 0 0 1 0 0 0 1. Okay, so I calculate its calculator. Okay, I can just use the so log
Mu value considered, Naresh. We said len 15 is there, no? Mu
yeah
value is there. 3.
sorry
Lambda,
this one
sorry.
lambda is
Uh,
3. Yeah, 3. Oh
yeah.
yeah. This is 3 by 5. Not yeah, this is 5.
Yeah.
Yeah. So it is log 15 is this divided by 5. That is 0.54. So it is it's anyway diagonal. So it's like, let's say sigma is diagonal. And what are the terms? So first one, so there is a plus this thing 0.541 542. And in the first term, it is 2 into 44 by 15. So it's 88 by 15. Some 5.86. And the second one is 8 by 15. So it is 8 by 15. So it is 0.533. Second, this is same 0.542, and third one is 0. So it is just 0.542. So it is 5.867 plus 0.542, 6.409. Second one is 0.533 plus 0.542, 1.075, 0.54. Okay, then they're asking the first invariant of.
Yes.
First invariant. So first invariant is just the trace. So first invariant of sigma is sum of all this. So this one plus 0.542 plus 6.409, some 8.026. Okay, so this is whatever MPA or whatever. Then they are asking third invariant. So it's the product of all these. So this is 6.409 into 1.075 into 0.542. So I3 of sigma is 3.734. 3.734. Then they are asking the hydrostatic pressure. So hydrostatic pressure is just 1/3 of I1 of sigma. So it is 8.026 by 3. That is 2.675. Yeah. So what are his answers? 15 is okay. 6.408, that's okay. 1.075 and 0.542, that's okay. And first invariant is 8.026. Okay, slightly different. 8.025 he's getting. Third invariant is 3.73.
Okay.
Okay, that's also slightly different. Maybe my pressure is also fine. 2.675.
Okay. Because of that
Maybe
J, no, I was not getting correct
I
answer.
think it's because of J only. Yeah.
Yes.
Okay. And your email, I'll reply. Yeah, I'll reply
Okay,
to it.
fine.
It's just similarly, it was just some.
I
If the
think
J,
similar
in case you didn't
very
consider J, that could have also got into that issue, right?
Yes, correct.
Yeah.
Yeah.
Okay. Anything else?
No, Naresh. Yeah, thank you.
Okay. Thanks. Okay. We'll see
Yes.
next week. I'll stop
Yes.
recording.
Okay.